Welcome to Deep Learning Talks. So today we are going to discuss gradient descent. We've all heard about this keyword gradient and descent. What does it signal? What does it mean? Where all it is used? Let's talk about it. So every loss function, every objective function has some sort of parameters. Now let's take an example of linear regression. If we are doing linear regression, what is the equation of linear regression? The equation of linear regression is y equals to mx plus c. Right now, when I compute the loss, let's say I take sum of squared residuals as the loss function. What is the residual? Yi minus yi hat, right? For every single data point, yi hat is nothing but mx plus c. So every predictive y is going to constitute some parameters in itself, right? So what that means is loss function or cost function, they're used interchangeably, the keywords, they're always going to constitute some parameters, right? Sometimes there would be M and C that are going to be constituted in the loss function. In case of logistic regression, we might have W transpose X plus B. In case of neural networks, we might have a lot of weights and biases in the feed forward neural network, right? And all of these are part of a loss function. So this is clear. Loss function will constitute and encapsulate a lot of parameters. What is the goal and objective of any machine learning algorithm that we're going to use? The goal and objective of the machine learning algorithm that we're going to use for any use case, whether it is regression or classification, is to minimize the loss function, minimize the cost function, right? We have fine-tuned, we have trained all of our algorithms to reach to its global minima, right? Now, the process of reaching the global minima, right? Let's just imagine that we are standing at the top of the mountain and slowly we are descending, we are going downhill to reach the bottom of the mountain. That bottom of the mountain, imagine that there's only one bottom. There are not a lot of bottoms. When there are a lot of bottoms, we call them local minimas. Imagine that there's only one bottom and the valley is U-shaped. Now this bottom is known as global minima. The process that will take us iteratively from the top of the mountain to the bottom of the mountain is going to be known as gradient descent, right? Now, where does loss function parameters come into picture? The mathematical intuition and the linguistic intuition says that we are going to optimize in such a way, we are going to minimize the loss function in such a way that the parameters that we will have are going to be optimal. And what are the optimal parameters here? The optimal parameters are those when the loss function is minimized, when we are standing at the minimum, at the global minimum of our loss function. Those are our optimal parameters. Now what that means is that we want the loss function to be minimized, and when the loss function is going to be minimized, the m's and the c's are going to be our optimum parameters, right? Now in case of linear regression, just imagine that we only have two parameters, m and c. We can use gradient descent, and gradient descent as an algorithm will help us optimize m and c. In case of logistic regression, let's say we have two parameters, let's say w and b. W is known as weight and b is known as bias, and we can still optimize them, right? So in case of neural network, let's say we have a set of parameters known as theta. Now, theta has a lot of parameters, right? I mean, theta constitutes of, let's say, millions of parameters. We want one deterministic way, one deterministic algorithm, one short way of describing a procedure that can help us optimize all the parameters. No matter which network am I dealing with, no matter whether I'm dealing with linear regression, no matter I'm dealing with logistic regression, no matter I'm dealing with neural networks, I want a short way to be able to optimize all the parameters. Now, optimizing all the parameters or getting the optimal value of the parameters and minimizing the loss function is an iterative process. You start at some random point and then you reach at a point that is a desired point. At that desired point, we call that desired point as, with respect to loss function, we call it as a global minima. With respect to parameters, we call them as the optimal parameters. Right. Now, let's talk about linear regression and let's take an example. Let me just share my video to take an example. Yes. So let's take an example of gradient descent with respect to linear regression. Now, as we talked about, gradient descent is not agnostic to the algorithm type. It optimizes and minimizes any loss function that you feed it to. Gradient descent works the same for all the loss functions. Now, let's look at here. In this case, what we're trying to do is, so we had a loss function and we computed the partial derivative, right? Let's look at the example. Let's look at linear regression and gradient descent both at once. We have a loss function known as sum of squared residuals or sum of squared errors, right? So we define it with respect to yi and yi hat. Yi hat is nothing but mx plus c, where m and c are our parameters, right? Now I need to optimize the loss function, the cost function. I'm using these words interchangeably, loss and cost, in such a way that my loss function is minimized. And at that global minima, I want the value of m and c, right? How do I do that? So the idea of gradient descent says that take the partial derivative of whatever loss function that you are dealing with. Supposing you're dealing with the loss function j, take the partial derivative of j with respect to m. Take the partial derivative of j with respect to c, and the gradient value that you get, the partial derivative that you get. Now, for example, this is what we get, right? We get the partial derivative with respect to m and with respect to c. So the partial derivative that you get, use this partial derivative in an update rule. Now, what does the update rule say? The new parameter is equal to the older parameter minus the gradient value into the learning rate. This is what the update rule says. Now, the best thing about this whole algorithm is that gradient descent stays same for all models, for all algorithm types. Like, it is not emotional that I will work good with linear regression, but I will not work well with logistic regression, and I will not work well with neural networks. The idea and the mental model for gradient descent stays the same, which is differentiate the loss function with respect to all the parameters and update the parameters and do it for iterations over iterations. If you're dealing with a convex function, you will reach the global minimum and you will get the best parameters possible, right? So the best thing is, it does not care whether you have one parameter or two parameters or three parameters or hundreds and thousands of parameters, right? So my linear regression can be multivariate. What I mean by multivariate is I can have thousands and millions and billions of parameters, and I can still use gradient descent to be able to optimize all of those parameters. Now, the intuition we talked about still remains the same. You're standing at the top of the mountain and you're going downhill, right? And as you go downhill, you will be able to reach a point that is your global minimum. And the kind of jumps, if you're very confident, you take higher jumps. That means you might have higher learning rate, right? If you're not that confident, you take lower jumps. That means you can have moderate learning rate, right? So you take certain jumps and keep on updating the gradient and keep on subtracting and updating your parameters so that you reach the global minimum. Now let's also talk about gradient descent with respect to logistic regression. Now, logistic regression has a different loss function, right? Above, we saw that we had sum of squared errors or sum of squared residuals. Here, the residual or the loss function is defined by the cost function j. J is a function of beta, right? So it's known as the binary cross entropy loss. Every loss function that we will ever see will always have, y hat, which is the predicted y. And the predicted y is going to constitute, it's going to be a function of parameters. Sometimes we might call the parameters as m's and c's. Sometimes we might call the parameters as w's and b's. Sometimes we might call the parameters as beta or theta. And we don't care how many parameters do we have. Do we have one parameter, two parameter, thousand parameters? We need a deterministic procedure that can minimize the loss function and give us all the optimal parameters, right? Sometimes we might only be dealing with one parameters. The problem or the challenge that is going to come after is going to be when we have nested parameters. We'll talk about it when we talk about gradient descent with respect to neural networks. But for logistic regression, the game is pretty simple. If you know calculus and you can figure out the partial derivative of this cost function with respect to beta, right? Now, what is beta? Beta constitutes as the set of parameters. If I know partial derivative and I can compute the partial derivative of the first term and the second term, and I can compute the gradient with respect to beta, then that is, that is my gradient descent. I just have to use the value that I have computed to plug and play in my update rule. And when I keep on updating, when I keep on updating the gradient value iteratively, iterations over iterations, this is known as gradient descent, right? Now, we have seen gradient descent with respect to linear regression. We've seen gradient descent with respect to logistic regression. The only challenge that we still should see is what happens when the loss function gets super complex, right? Now, in case of linear regression, in case of neural networks, we have something known as forward pass, right? Now, just imagine we have this neural network. Now, what is this neural network? This neural network has input layer, hidden layer, and output layer, right? Now, we have a forward pass. Now, forward pass will have W1 and B1, the set of biases at the first layer, and then we will again the forward pass for the next layer, which will help us, use W2 and B2, right? So if we realize, we would see that the final output The final output is the function of W2. W2 is a function of W1. W1 again is getting multiplied with the input, right? So we have nested parameters. In this nesting case, we need to unravel the computational graph, right? The computational graph has a topology, right? Now, what do I mean by topology? I mean by topology, what I mean by topology is that the loss function constitutes of output, which is known as A2. Now, A2 is a function of Z2, right? Now, what was Z2? Z2 was the output at layer 2. Now, Z2 encapsulates W2 and B2, obviously, and A1. A1 is something which is coming from the previous layer. Now, A1 is a function of Z1. Now, Z1 encapsulates W1 and B1. Now, in this case, computing the partial derivative is not super trivial, right? So, what we need to do is we need to apply chain rule, right? So, we need to unravel this computational graph and apply chain rules so that we can solve for nested parameters and the same algorithm that we talked about, which is gradient descent. What did gradient descent says? Take a loss function, let's say in this case, cross entropy loss, differentiated with respect to all the parameter value theta, right? Or for example, here in this case, the parameters are W1, B1, W2, B2. Differentiate the loss function with respect to all of these parameters, and that's it. So you are done. So you and then keep on updating the values. And how do you differentiate? Here we bring in something which is known as chain rule. In linear regression, in logistic regression, we did not need chain rule because we did not have nested parameters, right? So the only new idea that we introduced in case of neural networks is the idea of chain rule, because we have a computational graph of multiple variables and we need to unravel it and we need to use chain rule so that we can compute the partial derivatives in a mathematical manner which is very well applicable for computing the gradients, right? Now once we have the whole gradient set, we use that gradient set to update all the parameter set using something which is known as update rule. And this whole idea is known as backpropagation. So backpropagation in case of neural networks simply means that we apply gradient descent for all the parameters and we use something known as chain rule to update and compute the gradients. To compute the gradients and update the gradients, and we do it iteratively in a loop, right? So that we can still reach our minima, and at that minima, our loss function is minimized and we get the most optimal parameters, whether it is neural networks or it is logistic regression or it's linear regression or it is convolutional neural network or recurrent neural network or transformers. We are not emotional with the type of the algorithm. Okay, so the final closing notes are: gradient descent is basically just optimizing the loss function, taking the partial derivative of the loss function with respect to all the parameters and plugging and playing it into the update rule. So the update rule also stays same for all the parameter set. Let's say we assume that parameter we're talking about is beta. Beta is equal to beta minus learning rate multiplied by the gradient that we computed. That's it. So we have here now seen a mental model that uses loss function as an anchor, parameters as another anchor, and then an algorithm that iteratively optimizes the loss function or minimizes the loss function and gives us the most optimal set of parameters where we have the global minima for a loss function. I think that's it for now. And we will disambiguate gradient descent more and more when we go algorithm specific. Thank you.